Okay. Hello, everyone. We're going to let people trickle in a bit, but today we're going to be talking to you about the James Webb Space Telescope. Welcome to Universe at Home.
How many people do we have already?
I'm not sure. Okay, I think we should probably get started. My name is Tyler Barna. I am a graduate student with the Department of Astronomy and Physics at the University of Minnesota, and this is
Hi, my name is Bazan. I'm from Peru. I'm a student in aerospace engineering here at the University of Minnesota, and I also work as a teaching assistant for the School of Physics and Astronomy.
So today we're going to be telling you a bit about the James Webb Space Telescope, which is probably the biggest advancement in observational astronomy technology in the past 2 or 3 decades almost. Uh, but before that, I'm going to let Noe explain a bit about the history of space telescopes and why they're important for the field.
Right, thank you. So if you can pass on the slide. Right. So as you might know, as what happens is that the further out we look into the sky, like further out into space, the more we go back in time. So because of that, astronomers, scientists have a very much an eagerness and interest to look out into the edge of the universe to figure out what happened at the start of the universe. Because of that, there's a need for space telescopes. The reason why there's like this desire for this particular type of vehicle is that up in space, there's like almost no atmospheric turbulence. So what happens is that the atmosphere like causes a lot of turbulence due to the particles that are like bouncing around in the atmosphere. And that actually causes like much of the stuff around like that we look into the night sky to twinkle, such as the stars. Therefore, like if we were to look from the ISS, like the stars wouldn't be twinkling at all. Another thing is that wavelengths like gamma rays or like X-rays are not absorbed by the ozone layer, or like infrared are not absorbed by some certain elements such as oxygen or carbon or water in the atmosphere. Therefore, when we go into space, we can like measure much more wavelengths and get much more data from these different stars and galaxies. So, and additionally, the more we look back in time, the sharper we must get. So whenever we like look in materials that are like 13 billion years ago, like you need to get like a sharper image to understand like what is going on over there, at the origin of time. And this is not like something that we've been doing like very recently. We've been doing this since the 60s. So for example, over here, we have this telescope called Stargazer or OA02, which particularly has done a lot of observations on comets and novae. It was actually one of the first ones to determine like there's not only supernovas, like there's also novae, which like are much more smaller explosions that happen when stars like consume other star material and causes like nuclear reactions and small explosions around the star. And all of this like determines the groundwork for our current space telescopes. So we're going to be talking a little bit about that, particularly the four great observatories. So here we have like the great observatories, like those that have been like launched throughout the past decades by NASA and other entities to determine like stuff around the universe. So for example, we have Chandra, that is a space X-ray telescope. That one has been already 22 years in space since 1999. and is one of the only X-rays that have had like much more like much more power. Like it has had like 100 times more power than previous telescopes at the time. So because of that, it has been able to detect like emissions of X-rays from Sagittarius A, which is a supermassive black hole at the center of our galaxy, the Milky Way. And it has been able to like receive and detect shock waves from supernovae from distant galaxies. So the fact that we have this kind of observatory actually helps a lot of the understanding and how much time it actually takes for some certain like wavelengths to arrive to Earth, you know? Another one is an infrared telescope called Spitzer. That one has been focusing on the formation and also the birth of young stars in different nebulae along our galaxy. And it has been deactivated since 2020, unfortunately. Another one is also COMSAT that has had like multiple contributions in the gamma ray spectrum. So what happens with the gamma ray spectrum is that these ones are very powerful and usually come from like supernovae. So they have been, this particular telescope has helped in measuring gamma ray explosions from distant star supernovae. And this one has been active from 1991 to 2000. However, these ones don't come in comparison to the next one, which is the Hubble Space Telescope. So here we have the Hubble Space Telescope. That one is like the behemoth. That one is the one that we all know. That one has been working for 31 years so far and is still ongoing. Since 1980, this particular telescope has been able to help us have a much better understanding of like images of our universe in the visible light spectrum. So, and because of because of its huge diameter in this telescope, we've been able to do a bunch of research into deep space, particularly looking at the almost near the origin of our universe. And we've also been able to determine, like with that, how much the universe has been expanding. However, a couple of issues have already come with HST, particularly since it had been launched in 1980. It already has a lot of aging technology. And it's predicted that the emission will probably end between 2030 and 2040. And since we astronomers still want to look further out into the origin of the universe, this type of technology would not allow us to go even further. So because of that, new technologies have emerged that have helped us, that could help us reach that point, such as the James Webb Space Telescope, which Tyler is going to talk to you now.
Yes, the James Webb Space Telescope is an infrared space telescope, which is the most ambitious and expensive space telescope launched by NASA to date. It's set to launch in just a couple of weeks on the 22nd of December, and it's the first of NASA's next generation of major space telescopes. It will be followed by the Nancy Grace Roman Space Telescope, ideally in 2025. Noah mentioned the Hubble Space Telescope, and JWST represents a significant leap in observational capabilities compared to Hubble. The mirror size of JWST has an area of nearly 6 times that of Hubble, allowing for deeper observations of high redshift targets. On the right is the JWST Integrated Science Instrument Module, which is outfitted with 4 primary instruments. First is the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph. FGS functions as a guiding instrument, so JWST can remain on target, and NIRIS is a slitless spectrograph, which disperses the light of point sources within the field of view, creating multiple spectra. To explain, spectra essentially take the light of various elements and allow us to identify for a source that's emitting light, what elements it makes, or what elements make up the source, which is very useful in astronomy because it allows us to kind of identify what targets are like. Next is the near infrared camera, which is the primary imager for JWST. It's composed of two adjacent detector arrays and includes coronagraphs for viewing dim targets near bright objects. A coronagraph will essentially, it's a very fancy sounding word for something that will effectively just kind of obscure part of a viewfinder. So if you're trying to look at something that's close by a star, you can obscure the star so you can actually look at something that's close by instead of having the light from the star completely blow out whatever you're trying to look at. Next is the near infrared spectrograph, or NIRCam. It is another spectrometer with a unique microshutter array that allows for up to 100 targets to be viewed simultaneously, so dim targets that require long exposures don't monopolize observing time. Pretty much in a spectrometer, you need a slit usually that will kind of guide all of the light so that you're just looking at one specific target. NIRCam is unique in the sense that it has a lot of different kind of miniature spectrographs that all work together like an entire array. That will mean that they can, rather than just pointing it at one thing and only being able to look at that, it can just point in a direction and say, okay, I can look at this object here, and then with another part of the array, look at a different object, which greatly increases the efficiency of the instrument itself. Finally, there is the mid-infrared instrument, or MIRCam, or rather MIRI. It consists of both an imager and a spectrograph. It observes at higher wavelengths from 5 to 28 microns, and as a result, it needs to be actively cooled. It can observe targets at an even higher redshift than the other instruments due to its wavelength range, and it will provide medium resolution spectroscopy of many high redshift targets for the first time. Now, NASA has outlined 4 major science goals for JWST. First is reionization. JWST will be able to look far back in time and observe light from as early as 100 million years after the Big Bang, when the first stars began to form, triggering the reionization of hydrogen. With the use of spectroscopy, JWST will be able to explore exoplanets and the origins of life to determine the elemental abundances of exoplanet atmospheres and search for exoplanets where organic life might be viable. Next is stellar and protoplanetary system formation. Because JWST observes in the infrared, it will be able to observe the formation of stars and planets that are normally obscured by optically opaque dust. If we were to look at it with an optical telescope, the dust in between us and the target would absorb the light and prevent us from actually seeing any of the light that we want to be looking at. But the light that it emits in the infrared doesn't get absorbed by the dust, so we can see it. This image here is an example of planets just beginning to form around a star, observed by the Atacama Large Millimeter Array in Chile. Finally, there is galaxy formation. JWST will be able to look back at the first galaxies as well and analyze how galaxy formation in the universe evolved over time. We can compare the structure of early galaxies to those of present elliptical and spiral galaxies to determine how galactic evolution changed as the universe expanded. Given the ambitious goals of JWST, NASA created the Director's Discretionary Early Science Release Program to better utilize JWST. The first of the 2 early science release programs that I'm going to discuss is the Resolve Stellar Populations Project. This project is going to observe 3 nearby resolved stellar systems with NIRCam and NIRIS in order to develop point spread function fitting software for JWST and compile object catalogs for NIRCam and NIRIS. These observations will help to establish the optimal methodologies for several different types of local universe observations with JWST. Future research on stellar populations with JWST are going to greatly benefit from the documentation and tools provided by this project. Second is the Galaxies in Intergalactic Medium project. It's being conducted by a group of researchers that are also part of the GRISM Lens Amplified Survey from Space, or GLASS, program with Hubble. Building upon GLASS, this project will use NIRCam, NIRIS, and NIRSPEC to observe a gravitationally lensed galaxy cluster to explore the effects of early galaxies on triggering reionization, and will analyze how gas and metal abundances in galaxies evolve over time. As with the case of most of the ESRP projects, this project will also develop tools for data reduction and catalogs. with the use of these early science release projects, which will occur in the first 6 months of the observing time of JWST after it goes online, they will be able to generate various tools and catalogs so that future projects in the general observation cycle will be able to make more efficient use of their own time, since the amount of time available for observing is obviously time constrained. Noah is going to now talk a little bit about a couple of the general observing projects that are pretty interesting.
Thank you, Tyler. So yeah, aside from the other research scientific proposals um, that several scientists are doing with the James Webb Telescope, other observations are also going to be done. Particularly, one of the most exciting ones are in the field of stellar physics, because much of stuff happens when you're trying to like figure out like what happens during periods where a star goes under collapse and then explodes. So one of the stuff that the James Webb Telescope is gonna determine is how much is the loss of mass and massive stars, and how and what happens when they explode. So what happens is that, where does this mass go? Like, does it go into the black hole? Does it move around? It's something that's going to be determined with the James Webb Telescope. Additionally, there's going to be further research into massive neutron stars, and mostly a confirmation if there's the existence of them. How much is the limit of the particular mass of a neutron star before it turns into a black hole? And additionally, it's going to be taking a look at the origins of certain nebulae. So what's going to happen is that James Webb Telescope is going to be looking in the infrared spectrum and determine the origins of these particular nebulae, for example, the Crab Nebula. So to see like how does this particular star go into the explosion that now generated this beautiful thing that we can see in space. Next one. And also another one that is going to be pretty exciting is the large scale structure of the universe. What's going to happen is that the James Webb Telescope is going to do the first observations of the luminosity of galaxies that happened at 500 million years after the Big Bang. This is technically called the reionization era. So during that period, like there was a stagnation. There was like almost no formation of like matter, like large scale matter at all. For example, like stars and stuff. However, it's still something that astronomers have been like questioning and researching about for like decades. And with the technologies of the James Webb Telescope, it can be possible then we can determine like when how much luminosity was there like from these galaxies at this point in time. Other stuff would be determining like the amount of dark matter on small scales. So for example, if we were to take a look at a star that has like less than 8 solar masses. So if you were to see like a star that if you were to see a star that has like less than 8 times the mass of our sun, you would see still like certain spots in which you can see like presences of like dark matter. And what the James Webb Telescope does is seek to prove that. And last but not least, we're going to be with the James Webb Telescope looking at further precision on the Hubble constant. So in general terms, what the Hubble constant does is that it determines like the rate at which something is moving away from you. So let's say if you have a galaxy that is like 2 million years away, 2 billion light years away, it's going to be moving much faster than something that is like, let's say a star that is like 2 million light years away from you. So the further you are into the universe, like the faster you're going to see it move away from you. So this is what's happening in the universe right now. So it's going under a constant expansion. So what the James Webb Telescope is doing is seeking to have a much better precision of this particular constant. And if there is like in any other place in the universe, like a different kind of value for it, be it with like variables such as dark matter or like a particular bulge of mass in that particular area. So yeah.
Yeah, I guess kind of in summary, JWST is going to have wide-reaching implications in almost all areas of astronomy. We're rapidly approaching the launch in just under 2 weeks, and the ERSPs are going to be followed by general observing. In the first cycle of general observing, there's been just over 6,000 hours of research hours awarded to dozens of different research projects. And I will note a little bit, JWST is a time-limited project. I mentioned the MIRI has a active coolant required. Once that runs out, JWST isn't going to be able to function anymore. It has a very specific shelf life unlike something like Hubble. So things like the ESRP and GO kind of underscore how important it is that astronomers make efficient use of the time of the telescope and derive all they can out of this, extremely high power piece of technology. So, yeah. If anyone has any questions, feel free to leave a comment in the chat. We'll sit around for a minute or two just to see if anybody has any questions. I will say, while kind of waiting for questions, JWST actually very conveniently coincides with a lot of other large-scale telescope projects that are coming out of astronomy in general. There's a number of ground-based projects, such as there's a number of ground-based telescopes that are also being developed now that are going to kind of create a insane amount of data, and things like gravitational wave observations are currently becoming widespread. And generally, in the next 10 years or so, we're going to be able to see a very compelling growth in the area of observational astronomy. So, yes, I'm not seeing any questions in the chat, but yes, thank you, everyone. Have a nice evening.
Thank you very much.